Hello and welcome to Disseminate, the Computer Science Research Podcast. I'm your host, Jack Wardby. I'm delighted to say I'm joined today by Audrey Cheng, who will be talking about her VLDB 22 paper, TAOBench, an end-to-end benchmark for social network workloads. Audrey is a PhD student in the Sky Computing Lab at UC Berkeley, and her research focuses primarily on transaction processing for database systems. Audrey, thanks for joining us on the show.
Thank you so much for having me, Jack.
It's a pleasure. Let's dive straight in. So how did you end up researching transaction processing? What was your journey to this point?
Yeah, so now I'm a third-year PhD student at Berkeley, and I ended up here mainly because of my undergrad advisor, Professor Wyatt Lloyd at Princeton. My junior year of college, he has done a lot of work on transaction processing, and I was interested in doing research, so I reached out to him, and I ended up working on a project that extended Peter Bayless's bolt-on causal consistency paper. So in that paper, Peter looked at how you can go from eventual to causal consistency, and I sort of extended that hierarchy. So how we can go from like causal to sequential, and then from sequential to linearizability, and so forth. And I felt that was a lot of fun, just like thinking of protocols and coming up with new techniques to ensure stronger guarantees. So that's how I sort of fell into thinking about strong guarantees, and then that naturally led to transaction processing.
So let's talk about TAOBench then. Can you start off by telling us exactly what TAOBench is?
Yeah, of course, happy to. So TAOBench is an open source benchmark based on Meta's production workloads. Specifically, we look to capture the sort of request patterns, including transactional ones that you'll find on the social graph. And we feel this is especially exciting because I think this is the first time that a social networking company of this scale has open sourced their workloads, especially transactional workloads. So we hope it can definitely be a very helpful resource for the database community. And we've already seen impact both within Meta and outside of Meta for other databases.
You've touched on it a little bit there, but what is the motivation for developing a benchmark specifically for social networks?
So I've been interning at Meta for a couple of summers. One of my first projects was looking at adding stronger guarantees to their like social graph data store, TAO. This was a ramp TAO paper, which is in VLDB 2021 for anyone interested in that. But as I was doing that, one of the things I was trying to look at was how these transactional workloads operated at large scale and thinking about the needs of applications using transactions. And that's what helped me decide that I wanted to take a more holistic view at sort of what the social graph workload looks like. And because I had access to data, I thought it was really exciting. So I spent a bunch of time looking at different sorts of skew and also how data is stored on different shards, because explicit collocation is actually quite important, we found, for the social network workload. And as I was looking at these things, I realized that none of this was captured in other existing benchmarks, especially social network benchmarks. There are a couple, the prominent ones I'd say are LinkBench, which was released by Meta in 2014, but that was only focusing on the workloads of a single MySQL instance. So you lose a lot of the interesting patterns you see with geodistribution, and also at the cache level, which serves the majority of the workload. And also there's LDBC, which is a very important workload, but that targets mainly graph databases. So the focus here was more complex graph processing queries rather than the many serving requests we saw on TAO. So the majority of requests we have are like point reads and some point writes, but then you also do get some very complex queries and longer transactions, and especially figuring out the interaction between these and also on shared data made me really excited to study this workload and then try to open source it in a benchmark.
You mentioned the other benchmarks in this space. Are there any more other than LinkBench and LDBC? Like, how does it compare to something like TPCC or YCSB, something like that, right?
Yeah, great question. So in our paper, we identify like 5 properties that are important for social network benchmarks. And I think like TPCC and YCC are definitely important, like OLTP workloads, but they don't necessarily capture some of the properties we've seen on social graphs, including being very read heavy. Like TPCC is notably update heavy. And we also have extreme skew. We have very, very severe hotspots in some cases. Like, let's say Lady Gaga posts something, then a ton of people are trying to look at that post and like that post. So, and also the correlation between requests, and we also have different applications interacting in the same data versus most benchmarks. I feel try to capture the properties of one application. For a lot of different reasons, we felt there was a need for a new benchmark. It was not that TPCC or YSP are not important. They're very important points in sort of the workload space, but we felt within the social graph workload space, there wasn't a representative benchmark, and that's what we sought to capture with TAOBench.
Awesome. It's funny. I always, when I'm ever talking about like super nodes in a graph setting, I always use Lady Gaga for my example as well. I don't know what it is about Lady Gaga, but I always use that as well. Cool. Yeah. So you mentioned there's 5 properties there that you think should be captured by a social network benchmark. Can you maybe dig into these a little bit more, walk us through them, what they are, and say specifically why they are important?
So these properties were ones we came up with after like talking to a bunch of different engineers, industry practitioners, and also looking at the workloads and trying to identify why those are important for performance or other aspects of the system. So the first one is that we want to make sure we're accurately emulating social network requests. As I mentioned, like things like TPCC and YCSB, they're designed for a specific purpose, but they're not designed to capture the social graph. And because we have things like extreme skew, high correlation, redominance, it's important to design them specifically for the social network, which is a very important application domain and has had enduring popularity for maybe several decades now, we can even say. So things like Linkbench and LDBC are indeed designed, but not all benchmarks sort of satisfy property 1. And the second property is that we want to make sure we capture transactional requirements, and these can vary. So LDBC, for example, has full interactive rewrite transactions, while on TAO, the system has chosen to only support sort of one-shot read-only and write-only transactions because we found these were able to have improved performance and scalability given the challenging workload that at the moment is like tens of billions of requests per second. So serializability, like full coordination, is not yet feasible at this scale. And the third property is about co-location preferences and constraints. And we found that no existing benchmark actually satisfies this property. So what we mean here is like information about sharding and how data is stored. And we found within a real-world system that data placement isn't actually just an implementation detail, but it can reflect user intent, privacy constraints, and or regulatory compliance, especially with the growing concerns for data privacy and stuff. Sometimes it has to be stored in certain regions, and that can definitely impact how the workload is served and also have concurrency control and performance consequences. So we felt this was, to the best of our knowledge, no social network benchmark or most of the popular like OLTP workloads capture this data, and something we wanted to make sure that we supported. And the fourth property is about how we model these requests, and I think it also illustrates a trade-off in representing workloads. So most standard benchmarks take the approach of they want to represent specific behavior. So for example, they want to capture, I think one of the queries in LDBC is like you want the friends of friends with maybe some property, and like a very complex query, and you want to sort of capture the action of, okay, this is what would happen. So you have like these distinct query types, and LDBC has 29, TPCC, for example, has 5. We took an approach on the other side of the spectrum where we didn't attempt to capture any of these types. That's because on TAO, there's like tens of thousands of distinct query types running per day. So to replicate all of those and replicate the code would be infeasible. So instead, we decided to model these workloads using probability distributions without these prescriptive query types, which allows us to capture a much broader workload. But there's a trade-off of where with these distributions, if the workload changes, we're able to very easily capture that without needing to modify like specific queries. But the trade-off here is understandability. Like we are not able to sort of say, okay, these requests came from like this particular application doing this but that actually also helps us hide some of those privacy concerns, so we're not sort of highlighting exact user actions. So definitely it's a trade-off, but I think an interesting one. And for the most part, I think YCSB to some degree, LinkBench sort of also takes the approach of like using request distributions rather than query types, but not the most common, I'd say, approach that most benchmarks have taken.
Yeah, I know. YCSB kind of has that skew factor parameter, right, which you can vary to kind of, I guess, simulate that to some extent.
Exactly.
But yeah, anyway, sorry, yeah, continue. Property 5.
Yeah, and the final property is we wanted to make sure that the benchmark workload exhibited multi-tenant behavior on shared data. And this is important because when you think about the social graph, you might think, oh, it's like the Facebook application or something like that. But actually, there's a lot of different services and products running on the same data. So there's like Messenger, there's like WhatsApp, there's also like ads, for example, there's Marketplace, there's also now like the metaverse. So, and these are all based on the same users, like accessing these different applications. So thinking about the complex interactions between how one application can affect the behavior of another is really important. And I think the LDBC benchmark paper acknowledges this, that like you do need to capture this, but their approach was just to run mixed workloads, and this doesn't necessarily reflect how different applications actually interact in the real world cases. So it was exciting that we had this data at hand. We were able to study these and then also look specifically at like product groups, which are like sets of applications that share the same data, use the same infrastructure, and we do deep dives into how this behavior can vary both within product groups and across product groups.
To then satisfy these properties, you then profiled TAO, which is obviously Facebook's graph system. So can you maybe tell the listener more about this system and I guess why you chose it? But you chose it, right, because that is their system, right? And you were interning there, so that kind of answers itself. But yeah, can you just explain to us a little bit more about the system, what its architecture is, and some of the background on that?
Yeah, happy to. And I think this is important as well as why the workload, this particular system was of interest. So TAO, as I mentioned, is the social graph data store at Meta. So it stores and serves the vast majority of requests to the social graph. There are certain other stores, some like blob storage, for example, that'll store like very large videos or things like that. But for the most part, whenever you're accessing one of Facebook's applications, it's pulling the vast majority of requests and also doing serving those rights and stuff within TAO. So TAO has been around for around 10 years now. I want to say there's an ATC paper on the system published in 2013. And since then, it's grown a lot bigger. So currently it serves over 10 billion reads and tens of millions of writes per second on a changing data set of many petabytes. So it's operating like very, very large scale. It's distributed and runs in many different regions across the globe. And as such, I think it offers unique insights into the modern social network workload because we sort of have the majority of the social network requests like on this one system, and we're able to like look at the system and understand these request patterns. In terms of how it actually models data, so it has a graph data model, but not a graph data API. So it has objects which are called nodes and associations, which are edges in the social graph. And it was originally designed to sort of operate at large scale. So it didn't have any consistency guarantees originally. And it was the designers focused on like high availability and low latency. And as such, they also imposed a very simple API. So it's similar to a key value store, I'd say. But it does have range queries. So it has like point, get, range, and count queries, and then insert, update, and delete for writes. And then it since added write transactions, also prototype read transactions. More detail can be found in the RAMP paper about how those were added. But it definitely has, I'd say, some quirks as being such a large scale system. But I think because it has continued to run and continue to serve the growing workload for over 10 years, it sort of speaks to like this approach towards serving the social graph was successful. And It has a sharded tiered architecture. So Tao itself is actually like two graph-aware cache layers, and underneath Tao, there's a statically sharded MySQL database, and above Tao, there is a client-side cache. Also, there's actually many layers of caches, but the main one that we looked at was the client-side cache because that can a lot of like request to hotkeys end up being served from that cache. So it actually, I think it captures, we say in the paper, like 14% of the workload, so a significant portion.
What do Tao's request patterns look like? How do these actually manifest themselves? I know you said there's a large variety, but what is the sort of general patterns?
I would say at a high level, it is very, the requests are very read dominant. So I believe we said, so we looked for the purposes of the benchmark, we looked at traces over 3 days. And in that trace, we found like 99.7% are reads. So for the most part, people are sort of fetching data rather than updating data. And this is not surprising because like, let's say you're like loading posts in your feed. Once every post you load has a lot of different components. So you have to like read in all those components, and you don't like at least most people don't like every single post they're viewing. So you end up sort of looking at a lot of things before you send updates to the system. So that's mostly why it's so like read heavy. And also one thing we've noted is like the extreme skew. And this isn't unexpected because there are certain users in the social graph that sort of are much more popular than others. But even in the skew, we found that there's a lot of diversity that hasn't necessarily been captured in previous benchmarks. So one example of this is looking at hotspots. So we specifically studied read and write hotspots for both like normal writes and transactional writes. And what we found is that there are some hotspots that are like read to and written to frequently. So something like, let's say Lady Gaga actually posted something, that post would probably get a lot of engagement. But there are also other hotspots that are like write-only hotspots. So there's like a ton of writes going to these keys, but very few reads. And this could result from, there's often like asynchronous jobs running in the background, like maybe, or like migration tasks, or maybe like an AI or ML model like needs training data. So they're like getting this data and updating it in some sense, but not reading from it very frequently. These are reasons why we see these write hotspots, and they suggest that there's potential to further optimize sort of providing guarantees there, and also like convincing.
Is there a temporal aspect to things as well? Because I know, obviously, I've some experience with the LDBC stuff. We kind of have this notion of like spiking trends where you have like I don't know, someone comes in and posts an outrageous post on Facebook, and then they get cancelled, and then there's a massive drive of activity around people either liking that or commenting on it or unfriending them or whatever. Does that ever manifest itself in the request patterns? Or I guess it's only over 3 days, so maybe you didn't really capture that.
That's a great question, and something we definitely looked at. So at Meta, at least, the most prominent trend is there's like a daily spike in the workload that's like very noticeable when you look at these workload patterns. And it's sort of around, I can't remember what time around it is, maybe around noon, but basically a lot of people are accessing like social network applications at that time. So we see that spike, and we debated like whether to capture that or not, and how to think about like periodicity in the temporal part. So we found that while there are there's daily spikes, and also we measured different periods. So specifically, we looked at like July 4th versus a normal week, like 3 days around July 4th and a normal week. We found while like the volume changes, what we cared about is those probability distributions, and those distributions, including the tails, don't actually change that much across those different periods. So that's why we decided to sort of aggregate it across 3 days, because we wanted to focus on capturing those probability distributions. But definitely one of the future work that I want to look at is like, how can we think about looking at the temporal aspects and how that matters for like performance.
What are the parameters I have available to me when I'm so I want to go and run TAOBench? What parameters can I tune to change things, basically?
Yeah, so we have actually a small set of parameters, and we found like this small set was sufficient to fully characterize the social network workload. So It's nice because there's not too many knobs you have to tune if you want to run the benchmark. So I would break down the parameters into two broad categories. One is like they're pretty general and they apply most systems, and the second is the way that the second group of parameters are captured is unique to TAO, but the properties they're capturing are represented, I think, in most social graphs. So I'll explain those. But the first group are very general, like transaction size. So we have distributions for both the read and write-only transactions, and how and those can be tuned. We have different workload configuration files, so they've already been tuned for you if you want to run a particular workload. But if you wanted to try something else, you could change those. We also have sharding. So this determines what shards the key should go on for both objects and edges in the social graph. And this is sort of information that's available but not always used by different systems. So some of the systems some of the databases we ran against have their own sharding strategies. And there it's interesting to see how like a very skewed workload can be balanced or maybe not balanced across different shards. We also have operation types. So for the benchmark, we basically have like reads, writes. Writes consists of like inserts, updates, and deletes, and then read transactions and write transactions, and the proportions for those. We also have request sizes, so how much data we're reading or writing. This is also distribution. And so that's like the first category. And then the second category, the first is association or edge types. These basically capture particular integrity constraints on the social graph. So there are some cases where you always want like paired edges between two nodes. You don't want just one edge. So that's one property we capture. Another one is uniqueness. So between two nodes, you should only have one edge of a particular type. So these are important for things like, let's say you have a Facebook account, Instagram account, and you want to link those. You don't want to be linking like one Facebook account to like multiple Instagram accounts or something like that. And then there's also something called preconditions. These are essentially correctness constraints on operations. So while TAO doesn't support currently like fully interactive read-write transactions, you can still do something similar to like a compare and swap. If you first send your read and let's say you read X and the value of X is 1, and then you can condition your write on the value of X. So you can say, only allow my write to succeed if X is still 1. So it's, and in fact, basically an interactive read-write transaction, but they're not both within a transactional API, because sort of if you do that, then your read and then subsequent write will block everyone else. And it's really important, especially for reads, that those have high performance, which is why we currently have this format where the condition only applies on writes, but not the reads. So we're not holding up resources for too long. And then the final parameter is the read tier. So as I mentioned, TAO sort of has 3 tiers. Broadly, it has the client-side cache, TAO itself, and the database. And depending on which tier you're getting the request from, this can have very high impact on latency, like at least an order of magnitude is what we showed on the paper, I think. And this is information that also, like, depending on the underlying database, it might already have its own caching layer. In this case, it like wouldn't apply, but we needed this parameter to capture it on TAO to basically make sure that our workload was representative.
What's the schema of the social graph in Facebook? Is it kind of very similar to like a traditional labeled property graph, where do the edges have properties on them as well, or is that stored elsewhere basically? As
I mentioned, TAO is served by MySQL under the hood. Like MySQL is the bottommost layer, and since MySQL is a relational database, basically what they did is they converted both objects and edges in the social graph into rows. So let's say like an edge has a particular type that's just stored in a column. So you basically condition on that column, like only read that edge if it has a certain type. Yeah, so it's much closer to like a key value or like a relational than the graph database. Yeah.
My next question is, other benchmarks like YCSB, for example, have like standardized workloads. People can say I ran YCSB workload A. Have you the standardized workloads for TAOBench?
Currently, we have 3 open source workloads with plans to release more. So our workload. So our workloads are TAO, spelling out Tao. So the first one, T is the transactional workload. This basically captures the current transactional workload on Tao and sort of all requests that are under the transaction API. And then the A workload is the application workload. This represents the speculative transactional workload. So right now, we have a lot of applications that are sort of sending simultaneous reads and writes together, and they basically sending these requests with transactional intent. But because the rollout on the production system to using these APIs takes years, we're still in the process of sort of making sure everything is rolled out. So this workload is interesting because it has a longer tail than the T workload. So there's some like very large read and write applications that has heavier skew in some cases, and we've actually found this workload can be quite challenging from database for some systems. So it's been able to identify some interesting like performance opportunities. And finally, workload O is the overall Tao workload. So here we're focusing also on like the single point reads and writes. And this workload is notably read heavy as expected. Yeah, I think with these three, we sort of capture a range of interesting patterns on Tao, and we're hoping we can also release more.
Fantastic. So what metrics does the system compete on then? Is it just throughput and latency, or is there some sort of price per performance metric that you've formulated?
Yeah, at the moment, we are just focusing on throughput latency.
Okay, yeah, cool. As a user then, what is the benchmarking workflow? What do I need to implement to get a valid run of TAOBench?
So we definitely tried to simplify TAOBench as much as possible, and we made it very similar to YCSB in a lot of aspects, because YCSB had a lot of different drivers at this point, and we actually already currently support a lot of different systems. So if you want to run either like Postgres or MySQL compatible systems, there's already drivers for those. Or if it happens to be like Spanner, Cloud Spanner, CockroachDB, TiDB or UGByteDB or PlanetScale, those are already all supported. If you want to support a new system, basically what you have to do is you need to convert our requests, so like reads, writes, read transactions, write transactions, to the equivalent request on your system. So it's like a different syntax. Like Spanner has its own sort of query language. You sort of have to do that conversion because that's not present in our benchmark framework, but that process is pretty straightforward. So we have a website, taobench.org, and there's documentation there on how to do that conversion. It's usually pretty straightforward because our API is simple. This can usually be done in like an afternoon or two. It's not like a heavy process. Just basically, you want to make sure your system, where you're using like the right syntax for your system, and like converting our queries into your API.
Awesome. I will drop a link to the website in the show notes so the listeners can go and find that. How does it work with data generation? Do you have a data generator that produces all the data necessary for a benchmark run?
For us, the benchmark runs two phases. There's a workload generation phase, which we're basically preparing the database, and then the actual request generation. And we only do measurements during the request generation, though we've actually helped various databases identify things in the workload generation phase because we can run at large scale, and we sort of found some weaknesses in their systems during the workload generation phase, even though that wasn't intentional. What the workload generation does is we generate like a baseline social graph on which like subsequent requests can operate on. And here we basically insert requests, and if it's like a SQL database, insert requests into the system, and we create all nodes and we pre-allocate all the edges between the nodes, but we don't write all those edges because sometimes you need to test uniqueness and other constraints. So if you like pre-write those edges, then you'll never satisfy uniqueness because the edge like already exists. And you can also warm up the cache during this phase because we basically like send out create requests, and then we batch read back into the benchmark all the objects and edges we want to operate on. So that's in memory. And once that's done, then you can sort of run you only need to do this once for all the experiments you want to run on that particular system for a particular workload. So once you've done the generation, then you can run multiple experiments on that same data.
Cool. So how is TAOBench used internally within Meta?
Before TAOBench, the only way engineers could test different things was they had a very limited stress testing tool that wasn't realistic. It was like they could produce very basic patterns basically to validate something was like able to serve traffic, but there's no guarantees on that type of traffic. Or they could do shadow run. So they basically like try something out and then run it on existing production data. So they were really limited, especially in being able to test new workloads, because there was no way you could test a new workload unless you change something in production. But once you did that, you could cause issues in production. So they were like very, very cautious about what they were releasing to production. This slowed a lot of things down. So we talk about several different use cases in the paper. Before we discuss are like looking at new transactional use cases, looking at contention under longer lock hold times, if there's like network delays and things like that, evaluating new APIs, and also quantifying the performance of high fan out transactions. But basically, the general gist is TAOBench has now enabled us to test new features, optimizations, and reliability, which these might sound like standard things, but at scale, it's actually quite complicated. And without affecting production workloads, you still want to be able to test like realistic things. So the most powerful thing I think TAOBench enabled meta engineers to do is now we can sort of try out a new workload very quickly just by like changing the probability distributions and at large scale as well. And then from that, you can predict errors without having to wait to like very late stage in like pre-production or even encountering these errors in production. So one example is we have this like new transactional use case that was, I think, creating an object and adding an association, an edge in the graph. And we basically replicated the workload with TAOBench and ran it, and we found there were some contention errors. I think it had higher object contention than edge contention. It was still like relatively low, but we were able to like sort of measure these errors. And then when they actually rolled out this use case in production, they found the same breakdown of errors. So that was really exciting because it was able to validate both that TAOBench could capture these workloads in a representative manner, but also we were able to do this testing much earlier on and sort of foresee errors before it's like months down the line. And then you have to sort of figure out, oh, how do we fix that? How do we know we fixed that?
Is there any sort of continuous tracking of the type of workloads? Like, well, I guess what I'm asking is, has Meta's workload changed over the last, well, I'm guessing it has changed a lot over the last 10 years, but are they noticing changes now that you can then, I guess, model with TAOBench and say, okay, well, look, we're seeing things head in this direction. If this trend continues, this is kind of things we need to fix, or this is a potential optimization. Is there anything like that you can do with it?
Yeah, definitely. So one of the recent things I'm supposed to do is, so when the workloads we have right now were captured last year when we started working on the paper and on the benchmark. And since then, there's been a bunch of rollout of different transactional use cases. So I'm hoping to like capture the workload now, and it'll probably have very different properties than the previous one a year ago. So also like capturing those snapshots and seeing how performance changes, and if there are certain issues we should address now, like given the new workload. It's definitely something we can do with TAOBench, and is exciting.
So you said earlier on as well that the TAOBench has reference implementations for a number of cloud native systems. I guess the question here is, what is the impact of TAOBench being outside of Meta, and how did you go about sort of evaluating TAOBench's suitability to these systems and to help those systems study performance trade-offs and identify potential optimization opportunities?
As I mentioned, we currently support drivers for 5 different databases: Cloud Spanner, CrackerDB, PlantScale, TidyB, and UKBiteDB. And when we were like working on the paper, we basically wanted to show that our benchmark could have interesting results on systems outside of Meta. So we worked with engineers at each of these companies to run the benchmarks, and we were running on a cloud server, so hosted servers that they could monitor. So they sort of had full visibility into the results and also helped us in some cases like tune their system to get the maximum performance we could see. And I'd say there was like two main trends we were in ways we were able to help the system. One is that some systems did not benchmark as much as they should, just in general. So running a benchmark, especially a challenging benchmark on them, was able to quickly reveal a lot of performance bugs or opportunities that they were able to plug pretty easily. But also, I think the unique aspect of our workload is the skew and the asymmetric skew that we capture that is not necessarily represented even something like YCSB, where if you skew it, you basically for like the default case, you just increase the reads and the writes like proportionally. So you increase it to like certain keys, but for us, we have hotkeys that are hot for certain operations and not for others. And the skew, and because it's like very extremely skewed, we're able to help systems identify interesting trends. So I can talk about some examples of those. So for CockroachDB, they found one that, so we're running our benchmark on their Kubernetes like cloud cluster. But then when they ran it themselves against their bare metal machines, they found like a 30% performance improvement. That was because something about Kubernetes was misconfigured.
Oh, wow.
Their cloud machines are not
Jesus.
as well as they should have. So that's something they're fixing now. Something else I noticed is that because it's so skewed, they do have like an auto sort of sharding strategy to try to balance out that skew. But because the default of that, like at which point do you actually auto shard, is quite high. And it looks like at the overall workload rather than looking at particular hotkeys, because in our workload and what we've noticed in the social graph workload is like most keys can be pretty cold, but there are a couple of ones that are like several orders of magnitude, sometimes even hotter than other keys. They weren't looking at individual keys. So they ended up having, even if it's just a couple of hotkeys on one shard, that shard got a lot more traffic. Those hotkeys should have been spread out more evenly. So now they're exploring sort of better auto sharding strategies that are more sensitive to the particular keys the workload's running on. For TiDB, we have now been integrated into their like daily benchmarking sort of suite. So they run this benchmark every day, and they're using TAOBench to help them capture if there's any performance regressions as their system's still under active development. For PlanetScale, I think they're still building up their system, so they had some like limitations in certain queries. There's just like insert into select query wasn't supported, but we need this to enforce uniqueness constraints. So they're like prioritizing that, and I think it's now available actually because of our benchmark. They added that head of schedule. For UGoByteDB, we found a couple of issues. We helped them identify a couple of bottlenecks. One of them is when we like started running our benchmark on the system, their performance was like unexpectedly slow. So for all the systems except Spanner, we tried to run with the same number of cores to sort of get an estimate of like relative performance. Spanner doesn't really publicly say the number of cores we have, so it's sort of that comparison is less equal. But we found the performance was really slow for UGoByteDB, and we worked with them, and actually there was a performance bottleneck in their system they hadn't been aware about. So basically they use Postgres under the hood, and they've been using like a monitoring extension that was taking exclusive blocks. So it limited like the overall performance of their system. So they were able to get rid of that. And then they also were doing something weird with scans where we had like, because we were batch reading, we had a filter, we had a limit on sort of the number of rows we were scanning, but they were actually pulling all rows in a table into memory on every scan. So that quickly fell over and led to out of memory errors. So they are now, I think they fixed that already. That improved their scan performance by a lot.
Nice. So I guess, are there any situations then though when using TAOBench might be like the wrong decision for a user or for a database system?
Yeah, I would say there isn't necessarily like when it's wrong, but it depends on sort of what.
Yeah, I should have phrased that. I should have phrased that as suboptimal, not wrong.
I'd say it really depends on how you want to be stressing your system, because benchmarks at the end of the day are tools that we are using to better understand the performance of our system. And I think TAOBench can look at those aspects in a very interesting way. But for example, we are much more read heavy than write heavy. So there are certain workloads, ones that TPCC is very good at, for example, that are very update heavy. You have a lot of like read, modify, writes, and those can have significant performance opportunities. It's not to say that TAOBench cannot capture those workloads. Actually, if you like modify those distributions yourself and let's say like focus very heavily on like writes and write transactions, you can capture them, but they're not like the default use case, I would say, of TAOBench. And that's the reason I feel like we have so many different benchmarks. It's because people found, oh, like this benchmark captures one aspect of certain workloads well, but it doesn't capture other aspects. So let me like go and create a new one. With TAOBench, we tried to be as general as possible so that hopefully if we can get interest from like other social network companies in the future as well, they can like add their workloads to our framework because it's very general. But we are sort of targeting, I'd say, the social graph workload space.
Cool, yeah. And I was going to ask kind of what are the limitations of TAOBench, but I guess maybe it's been captured by that.
Yeah, I think most answer, the one main thing is we currently do not have interactive read-write transactions because those requests are not present on Tao's workload, but those would be very easy to support on the benchmark if like those are added in the future or those are something that other like users wanted. But yeah, that's not currently available because that's not captured in Meta's workloads, and our starting goal was to be representative of like Meta's production workloads.
What is the most interesting and perhaps unexpected lesson that you have learned while working on TAOBench?
Yeah, I would say that a couple of interesting. So one is definitely the diversity of request patterns and skew and things like that I observed, like looking at these real workloads. People can use, I would say, even like abuse the system in very not standard ways, because as an academic, usually we're taught like these are the best practices and this is how you should like use database. That's very not true. Yeah. So like one of the things we observed, for example, we looked at like contention, specifically like write and read contention, because there's no blocking reads on Tao currently, so there's no like read-write contention. But we found like I think it was like more than 97% of write contention is intentional. Basically, the application knows what it's doing is going to cause a conflict, but it continues to do so because it knows the system will, like, let's say it like sends a bunch of concurrent requests and it knows only one of them will succeed. And it can rely on the system to do that. So it will sort of write this as a expensive code for the system because it knows that it's safe to do so. So I think that was very surprising. And there's been a point when I started like researching transaction processing binary PhD, which I felt this is like such a well-studied field. I've done everything in the 1980s. But I think now looking at these different workloads and these extreme cases, there's a lot of different problems that people haven't considered simply because they didn't have access to like the data and the workload pattern. So now I'm really excited to leverage TAOBench to sort of hopefully inspire new research problems.
So yeah, I guess from the progress in research is very non-linear, right? There's lots of ups and downs. So from the initial conception of the idea for TAOBench to the final publication, and were the things that you tried in that process and kind of dead ends that you went down, so things that you failed that maybe the listener might find interesting?
I think one thing is like figuring out that set of parameters took a lot of trial and error. We had two approaches that we could tackle from. One is we start sort of with a list. We start simple. We start with things that we know would probably make sense to include and then build it up from there and go trial by error. Or the other thing was like we come up with an exhaustive list of features and like use an ML model and train it and see if it will fit. We decided to go with the first one because it was like more understandable and explainable. And I think even in some cases, the ML model doesn't always capture especially like extreme skew and things like that, it might not always be accurate, which is why but the first approach required us to like manually sort of try out new features, build it out and see what works. So we did actually look at like temporal patterns and something I think we discussed earlier, and we thought that would make a difference, but it didn't actually impact the access distribution, only the volume. So that's something we decided to put off for the paper. And then, yeah, I think that was definitely a lot of trial and error. And then also when we tried to get TAOBench running on other systems, for them at that point, the code was already pretty mature because we'd run it internally, but there were still some kinks we had to iron out. And as we like worked with the database engineers from the various companies, they also gave us feedback. They're like, oh, this isn't as clear as it could be. So we also ended up making a lot of, they're more like not modifications to the core logic, but sort of to make the code easier to use. There are a lot of changes there. And also running the benchmark on each of the systems was definitely a process, because even though the code development didn't take that long, it took many iterations for almost all the systems to figure out if we were actually getting representative performance, because the first run was like never good. So then you have to keep iterating and seeing, and then you get to a place where you feel it's pretty reasonable, but we wanted to make sure we captured as representative results as possible. So there's a lot of back and forth, with each of the 5 databases. So it was definitely a lot of work, but as you'll see on the paper, there's a lot of authors. I had fortunately a lot of undergraduates at Berkeley who are very passionate about research, and they helped a lot with that sort of development process.
So what's next for TAOBench? I know you've spoke about it briefly across the course of the interview, but what are the highlight things? What's the initial next steps and the big picture goal for it?
Yeah, I think we're open source now, which is exciting. We like jumped through all the legal hurdles and stuff. We're definitely trying to do more PR for it and get more people to use it. It's exciting that like the databases we worked with have already like seen value in the benchmark and are starting to integrate it into their systems and make it like actively use it as a part of their development process. And we're hoping to like build out the community there. I think another aspect is like what workloads are available. So as I mentioned, the workloads we have currently are from like 2021. And we're hoping to like do a refresh sort of on those, release more workloads. And as a part of this, because I've seen different patterns, both in terms of like the skew and also like the long tail, sometimes you have like very large transaction use cases. I feel there's a lot of interesting research questions relating to concurrency control. And I'm excited to pursue those going forward.
Can you briefly tell listeners about your other research as well, things like the ramp tower?
Yeah, happy to. So I'd say, broadly my research is focused on like transaction processing with some focus, I would say, like large scale systems. So the previous project to this TAOBench that I worked on at Meta was called RampTAO. This was ensuring read atomicity for the large scale system. So basically how we can add a stronger guarantee without impacting current applications and with like low performance and storage overheads. I have a paper and a talk available on this on my website. I think they're both linked on my website. And then I also have another project that we're in the process of submitting right now on looking at how transactions and caching interact as well. And that project actually uses TAOBench workloads. But yeah, we're hopeful that with TAOBench, we can hopefully inspire some of my own research, but also help other both people in academia and industry highlight sort of new problems and ways to address them. But I think the goal of the benchmark at the end of the day is to sort of help you understand your system and what its limitations are so that you can improve it.
If you could kind of say something about how you approach idea generation and selecting new projects and what your process is for doing that, how do you choose what to work on?
I'd say as a current PhD student, I'm definitely still figuring that out.
Yeah.
But I would say what's worked really well for me and what I prefer is, I think being inspired by real world data and problems is great, because you have sort of the grounding that this is this is a problem to at least like some real users. Not necessarily to say like that should always be the case, or you should only look at the problems that industry often use, but sort of looking at that to understand the general trend of why current systems cannot perform to that degree, and then using that to, my goal is like to try to understand that problem, and then once I have a sense of that, to think about different ways to solve it. And I think being in academia gives me the freedom to sort of think outside of the box of, oh, we need to like implement this right away, but this maybe would be like harder to implement in a short amount of time, but it's a good like long-term solution. So yeah, I think for me, like looking at the real world aspect and using that to inspire you but not necessarily limit you has worked well.
So what do you think is the biggest challenge in your research in transaction processing now? What do you think is the biggest challenge facing us?
Yeah, I think that while there's been a lot of academic work on sort of how we can deal with certain like high contention cases or things like that, a lot of those you find are not applied in practice. Like on TAO, for example, they use two-phase locking and two-phase commit, which have been around for decades.
The most classical setup going, right?
Exactly. Like there have been hundreds and thousands of papers on like things that perform better theoretically than two-phase locking and two-phase commit. And I think one of the reasons they're not applied is because 2PL and 2PC are like so simple and understandable. So I think there's a need for better performance, but also keeping in mind the simplicity and what's actually feasible to implement in practice.
So last question now. What is the one key thing you want listeners to take away from this episode and from your research?
I'd say the key thing is that with this new benchmark, TAOBench, which captures Meta's production social graph workloads, we've been able to have impact both within Meta and outside of Meta, and it provides sort of a stepping stone, hopefully a lot more exciting research on transactions and concurrency control, and I would encourage you to check out our benchmark.
Brilliant. Well, let's end it there. Thank you so much, Audrey. If the listeners interested to know more about Audrey's work, then we'll put all the links to everything in the show notes, and we will see you next time for some more awesome computer science research.